We are waiting for some few seconds so that everything is connected. So I don't know if you heard my first good morning, everyone. So good morning, everyone, again. We will be waiting for just some second for everybody to connect and the actually recording of the webinar to start. So it's really nice to be with you here this morning with Simone. So actually, we will be starting our presentation just now. Perfect, it should be all right. So I'm sure that people will join slowly in the next few minutes. So we are here this morning to actually discuss about laser powder bed fusion, which is a pretty hot topic actually for us at Skylabs, and obviously it is also the main work of what Presix is doing all the time. We are actually having this project, AmLabs, with BIMIT in the last 2 years, and we were very happy actually to have this project in which we have demonstrated that we can reduce hot cracking with beam shaping. So we will be discussing those results today. So I'm Gwen Pallier. I'm product line manager at Skylabs, and I'm here this morning with Simone. You can introduce yourself.
So thank you, Gwen, and really nice to have you, everyone. I'm Simone Barani, R&D manager from PressX, that is a small company part of the BIMIT group.
Okay, so we will, of course, be introducing both companies shortly in the next few minutes. Just want to say that actually this webinar, in this webinar, you have actually a chat on the right. So if you have any technical issue, you cannot hear us, anything, don't hesitate actually to ask in the chat. We have Clementine, who is also hidden somewhere and looking at all the questions, and that she can definitely help you if there is anything you need. And if you have also questions along the way, we won't answer them in live because it's too complicated. So we will just go through the presentation. But at the end of the presentation, there is a Q&A session. So we will be answering all of your questions at the end of the webinar. Please do not hesitate, ask them along the way in the chat, and we will be looking at that in the end. So what is our agenda today? Well, of course, we will start by describing a bit what the AmLabs project was and what actually challenges we wanted to take up with that project. Then we will be describing what Skylabs is doing and what solution we have provided on the project. Then it's going to be Simone presenting Presix and what they are doing and what actually process results were obtained in Italy. And we will conclude and go to the Q&A session. So I will actually try to make it pretty interactive and to make a lot of surveys so that on one side it's keeping you awake, and on the other side it's actually very good for us to know who we are talking to. So we will be actually looking at the challenges of laser powder bed fusion, and we will start by a survey. So if you give me a second, I will try to launch it. Should be that one. So you should be having it on your screen, and you can actually, you have maybe to scroll down to have the answers. You should actually be able to click on multiple answers. The idea is to give us an insight on what for you is the one challenge or the multiple challenges that you would like to address with beam shaping in laser powder bed fusion. So I'm going to give you some 1 minute or something to answer. So my suggestion, I maybe should have taken another option, but what we have heard from the market for now is that there is an interest in improving the process speed, in actually improving the quality, like hot cracking reduction, in also printing new powders, which were a bit complex to actually print. Increase the precision is also somehow a challenge that I've been hearing about, and tune actually the composition of the printed parts. This is also a topic that we've been hearing about. So I think that more than half of you have voted already. So I will just give you some more seconds to answer, and then we will be sharing the results actually. Okay, so I guess we will just give you 5 more seconds, and we will be sharing the results. Okay, so we should be now sharing the results. Maybe again, you have to scroll down to look at the results actually. So actually 70% of you have voted, and it's actually pretty cool because you have mainly voted for 2 challenges that we definitely want to address at Skylabs. One is improving the process speed, and the other one is actually improving the quality. So now at Skylabs, we have actually a pretty clear strategy on how to address those 2 challenges. We may be looking also at others, of course, but these 2 ones are very important, and definitely you're right to say that we can actually address them with beam shaping. So let's get back to the presentation now. And explain to you what we are doing in that one project that we were having with PresX. The idea is actually to improve the productivity and to allow new material processing, I would say in general. And we were looking at that actually thanks to beam shaping to reduce the thermal gradient. That was the main idea of the shape that we wanted to try, which were actually based on what we were finding in looking at what different papers were published with from academics mainly. So the idea is to have a more stable process to enable higher scanning speed, but to also to reduce the number of rejected parts, and to that would be like the ultimate goal, to reduce the post-processing time. And that is actually what Simone can give you a better insight on later on. So the idea is actually to be focused on one topic because it would be too complicated to address, for example, all powders inside one same project. So we were actually looking at nickel-based superalloys powders and how to improve the processing of those powders. So a short word about this project. It was actually a PulseAid project. It's European funding. And this project is just two partners, one technology provider and one technology adopter. So WIKI Labs were providing the technology, which is based on multiplane light conversion. And PresX is actually adopting our technology and installing it in their very nice workshop in Italy. So the name of the project was AmLabs. And I will be again asking a lot of questions to you. So if we want to see what we were doing is actually relevant to you, I also want to know what you are using in your machine. So we will go to survey number 2. So survey number 2, give me a second. Which should be now on your screen. What laser are you using most of the time? It's again a multiple choice. So I would say that at least you have to pick up two answers. One is on the power, one is on the number of the lasers, but you can actually pick up more than that. I would say that power, there are three ranges of power which are used. People are either using around 200 watt sometimes on some machines. Then there are some machines actually with 500 watt lasers, and it's slowly starting to have machines with 1 kilowatt lasers. So it's actually good to know who is using what. And similarly for the lasers, I did choose 1, 2, or 4 lasers, but actually I know now there is a one very cool machine made in Germany actually with 2 lasers, but I'm not sure many people are using it for now. I think it was just released recently. So you can only choose, unfortunately, in between 1, 2, and 4 lasers. So since I know that I have actually another one survey just following, I'm not going to give you so much more time to answer. So you can have just one more, not even one more minute to look at this one. And I will be actually sharing the results. So it's pretty spread actually. So, but still there are people who are using 1 kilowatt laser, as you can see. You may have actually to scroll down to look at the results. So half of you are using, I would say, less than 500 watt and half more than 500 watts. So in this actually webinar, we will be discussing the result that we were having with a 200 watt laser. It's important to say that definitely you can get exactly the same kind of results with higher power laser, and especially if you are focused on the yield improvement and the processing time reduction, it is the more the power you use, the more efficient beam shaping will be. But we can get back to that later on. So I will stop sharing the result and ask you one last question. Then I'm getting back again to the presentation. It should be sharing. I want to know what focusing optics you are using, because it's also very important for us that we work with the right focusing optics. So what we were using in this project, and it's I can use the time to answer, is actually an f-theta lens, because it's pretty common in all those machines. But there are also nice systems which are called 3D scanners, which are also pretty used in the market, and we are hesitating on what we should be using for our next test. So I'm hoping that you will give me my answer in that survey on what I should be using, because we plan to do some tests with actually the ILT this time around June. And we actually plan to go for 3D scanner. So just want to check if it's also what you're using. So I will just stop the vote now and share the results. It's terrible. You're not helping me at all, because actually 50% of you are using 3D scanner and 50% are using the 2D scanner. But at least I can see that both are being used. Pretty nice. I'm not going to be asking you questions all the time. Don't worry. Huh? So we are getting back to the presentation now. And I will be actually just presenting shortly WIKI Labs and what we have actually provided inside this project. A short word about the company. If you've registered to the webinar, there are good chances that you know us already, so I will be short. But basically, I can say that we are actually doing R&D development related to beam shaping. So we are really developing the systems from scratch, I would say somehow. We are also manufacturing them. So actually you can see on the very beautiful image on the left, our new buildings in Rennes, which we are so happy we are in for now, like 8 months, and they are made for us, and they are actually made for manufacturing. So it's really cool for that. So we do all the systems in Rennes, manufacturing and assembling. And then obviously we are actually a privately owned company, so we are actually trying to sell them as much as we can. So what is Scalabs? I just have to insist on I guess I would say one thing is that what we are doing is actually based on multiplane light conversion, which is a unique technology which was developed more than 10 years ago now by our CEO. And I will describe the technology later on, but it's important to remember that everything we are doing is actually based on that technology. We try to apply that technology to a lot of different applications. We started with telecommunication at the beginning of the company, and you can actually see that pretty easily that the 3 product lines in the middle of the slide are all telecommunication for different application. The coolest one probably being now laser communication. We are doing a lot of optical ground station to communicate with satellites, and this is actually a pretty cool application. We are also doing a lot of defense. That's what you see in the custom product line. But today I'm here to discuss laser material processing and how we can apply beam shaping to industry actually and manufacturing. So we are working with both high power CW lasers and ultra short burst lasers, and in both cases, actually, we are trying to have standard products and customized solution. I would say that LPBF for now is a customized solution, meaning that we don't have any standard references for that, for example. But we plan to release something in Munich in June. So one day it's gonna go from customized to standard solution. So it's a good news for you because it's gonna be faster to get the system if you want to have one once it's an off-the-shelf product. But anyway, you can always customize it. It's kind of our DNA at Scalabs to customize systems. We apply this system to actually a lot of different applications, and I'm actually pretty happy to say now that we have actually demonstrated in each of these single application that it can be useful to use beam shaping. So that's the last time I'm asking you a question, but it's a very important one somehow. Have you ever tried beam shaping to improve laser powder bed fusion processes? And actually, you have to give me 1 second to share the last survey. It should be now on your screen. May I have to scroll down? Less choices. The first one is no. I'm pretty sure there's going to be a lot of no. And then you just have 2 options. Is either you have tried what is actually now being pretty spread somehow in different R&D labs and application labs is the beam shaping through the fiber of the laser. The most popular one being probably Enlight. But there are people who actually did try also other technologies. I would say hopefully many of you have tried MPLC, but I know how many of you have tried it. So I'm not going to learn much on that. But there are other ways to do it than MPLC. You can have used also maybe DOEs. There are been some projects with DOEs. Okay, so I'm going to stop the voting now and share the results, and that will be it. So what you can see is that actually only actually 20% of you have been trying the Enlight laser, which is, I expected actually more. But anyway, I hope all of you will be trying MPLC soon. That's the main point to remember. And still, a third of you have not tried actually anything yet. Okay, so let's get back to the presentation. I will just give a short word on the technology because, as I did say, there are many ways to do beam shaping. One is actually through the fiber of the laser, having what is generally called a dual core, or having just 2 core, one inside core and one ring core. But there are also DOEs, SLM, a lot of interference-based system. And if I have one thing I want you to remember on beam shaping and beam shaping technology is that if you use a different technology, you will get a different result. Just trust me on that. Depending on how you are doing it, you may have actually exactly the same shape in the processing plane because it's somehow not that complicated to get the good shape in the good processing plane. What is actually complicated is to have it robust, to have it stable, to have it compatible with your environment. And actually, one very important point that we are actually focused on a lot in K-Labs is how it's actually behaving, how it is 1 millimeter above, how it is 1 millimeter after. And this is like so important if you want to have an industrial systems. So don't just look at how it looks like in the processing plane. You have to really consider the whole beam and how it's propagating. And what actually we are doing with MPLC, and I'm going to go to my slide about MPLC, is we are using a lot of faceplates one after the other. There are so many possibilities to do that. So what we were doing is actually what's in the image on the left. 10 years ago, it was faceplates one after the other, slowly changing the face of the beam to enable any kind of shape, freeform beam shaping. We could basically do anything. Is it useful to do anything is another question, but we could do anything. Along the way, we realized it was not so convenient to do it in a refractive way, so we are doing it in a reflective way. So we now have the light which is going back and forward two mirrors, as you can see on the right, and one of them is actually being textured. That's what we are manufacturing here in Rennes and assembling. What you can see here is actually a system which is made for telecommunication. I did say we actually do a lot of telecommunication. So that's why you have all these fibers at the input. The idea is to combine all of them inside one, all this monomode fiber inside one multi-mode fiber. So what you can see here is that it's actually fully passive, which is good to have something which is robust. It's fully reflective. This is also very good if you want to handle high power and high energy, and it's actually useful for a lot of things, like reducing focus shift, preserving the spectrum of your laser, things like that. You can actually shape multiple beam at the input. It can also be multiple beam at the output, and both can be either fibered, either free space. So that's actually it for MPLC. I will be short on what we have done with actually PresX. So the idea was to test three different shapes. So I did say it's based on literature. We did look at what was actually working, and we wanted to have that integrated inside a real machine and test on Inconel printing. So the first one was an elliptical shape, and the idea is actually that you manage the thermal gradient differently depending on the scanning direction. The second one is like so classical, it's the ring. So in the end, we were doing a ring of 150 micrometer diameter. It's easier to say it now that the project is finished, but if I have to redo it, maybe I would be doing a little bit smaller ring because we were having only 200 watt. And I am saying that because actually we could do it. We could do smaller ring, we could do bigger ring. That's one thing which is very important. Somehow you have to adapt the shape to your laser power. And that's what K-Labs is capable of doing, and which is also so important. We are not stuck to one shape. We could do any kind of shape, a larger, thicker ring, larger ring, something in the middle, nothing in the middle. We could do anything. But we have tried that one, and it actually somehow worked at PresX. And the last one is the top hat. So we were doing a 90 micron diameter top hat that was also installed on the system. So the idea for now was we have one system which is providing one shape, and we were actually exchanging the optics inside that system to go from one shape to the other. That's what we were doing. It was our very first prototype in the project. What we will do in the future is different, but I will get back to that in the end of the presentation. It's now time that I stop speaking and I leave Simone continue on the presentation.
So thank you very much, Gwen, and for the really nice presentation of the project and of the companies. And again, I'm Simone Barani from PresX. PresX is part of a larger group. I'm sorry if I'm going to be a little bit boring in the next slide, but unfortunately we are a quite large group, and I just want to show all our capabilities. So starting from that, I will introduce a little bit our group. PresX is part of BIMIT Group. BIMIT Group is a large group specialized in metal additive manufacturing, and it's made up three companies basically. That is BIMIT, the biggest one, and PresX that are in Italy, particularly in Parma and Reggio Emilia. And then we also have a company in UK in Thatcham that is 3D additive manufacturing. At the end, we have several different metal additive manufacturing machines, and we also have more than 30 post processes, more than 100 employees, and several dedicated plants. Our focus is basically on reliability on different in different industrial fields, and so we are in general producer of additive manufacturing parts. We are certified as 9100 and 1001, We also have the A8 IATF 16949, and we also have accreditation for an ADCAP for the heat treatment and some laboratory testing. The idea behind the BIMIT group is to offer to our customer a one-stop shop solution that basically starts from the pre-manufacturing of additive manufacturing part that we have engineering and design. I don't know how comfortable are you with the additive manufacturing process, but once you pass from a more classic manufacturing and you want to go to additive manufacture, you have some points that you need to take in account until we help our customer to engineer their part in order to design and obtain something that is correct to be printed, to be additive manufacturing printed. And so starting from the pre-manufacturing, then we have the AM prototyping and production. And then following to that, we have all the post-processing, where we have heat treatment that unfortunately is missing, but we also have heat treatment. We have hipping, welding, CNC machining, surface finishing and coating. And at the end, we also have testing and inspection. Our printing capability is let me say it's quite large. We have several choices of metal machines. And in general, we are focused on laser power bed fusion ones, but we also have two EBM Arkham. And also for the metal alloy choice, we have several. Additive manufacturing is not famous to have such a large quantity of different materials that you can manufacture. In particular respect to more classic manufacturing processes, but depending on the plants, we almost cover all the alloys that you can see here. And in particular for this project, the focus was, as Gwen correctly said before, is the Incon 939. Instead, regarding the heat treatment, we have 3 vacuum furnaces in class 2 regarding the AMS 2750, and they are NADCAP accredited, and 1 air furnace that allow also the oil quench. Then following to the hipping. Hipping is a quite old technology that we use in general for casting of aluminum. But what we are trying to do is to shape this kind of technology for a more actual use, that is additive manufacturing. And in particular, we have installed the Quintus system with the uniform rapid cooling that allow to have high pressure up to 200,000 bar and 1400 degrees Celsius. But the very interesting thing is that the control cooling rate is up to 1500 degrees per minute. And all these features are in uniformity class 2 according to the AMS standard again. And then we offer different solutions regarding surface finishing, and starting from the more classic one, such as blasting or manual, to more complex, such as chemical milling or vibro finishing, reaching to the super finishing process of dry light. That is a technology developed by GPA Innova in Spain, but we are a developer of the technology, and we also sell the machine. And this is a solid solution for finishing, electrochemical solid solution for finishing that allow to reach super finishing at the end of the process. And then concluding, we have the laboratory that at the beginning it was born to be part of the additive manufacturing process. So we are focused on the powder, and in particular powder analysis such as granulometric or physical or chemical analysis. And then we are moving to a more complete laboratory testing, adding mechanical testing, metallographic analysis, and failure analysis, CT and NDT, and also cleanness. This was just a short presentation of our group. And now we can go to the result of this project. For this project, we have installed the BIM Shaper developed by Kylabs in one EOS M280 machine. That is a quite old machine, respect to all the other that we have, and also in general regarding printing machine. But the idea is try to understand if we can print a material like Incon 939 of an old machine. We currently print Incal 939 on your machine that have a different amount of power. For the EOS M280, the maximum power is a 200 watt, and it's a single laser machine. So in this slide, you can see on the left the EOS M280 that is open, and the system, the beam shaper, is installed. And in order to have the laser, then we have the laser source that is directly connected to the beam shaper, and then it's going to the laser scanner. We have installed the 3 different beam shaper, and we have explored the properties of the material. In particular, the quality evaluation was focused on 2 parameters that are porosity and the presence of cracks. The printing process is quite, let me say, fragile system. In general, you have 4 different parameters that you can tune. That is the laser power, the scan speed, the hatch distance, and the layer thickness. If you're not so comfortable with additive manufacturing process, I will introduce briefly with other one. Well, laser power and scan speed, it's basically the power of the laser and the velocity of which the scan of the laser moves. And then you have hatch distance. This is the distance between 2 parallel passes of the laser. And the layer thickness is the quantity of the thickness of powder that you're putting every steps to create your part. For all the 3 different beam shaper that we have tested, we have performed some specimen on the base plate in order to evaluate the presence of porosity and cracks. Unfortunately, for the elliptical one, the result was not good. We did not find a set of parameters that allow us to produce a part with low porosity and no cracks. So you will not see the results of this shaper in this presentation, but because basically the result was not good. So we go directly to the ring shaper we have installed, and we have tuned just the scan speed. Reason why is that, as I said, it's a quite fragile equilibrium in order to obtain a high quality component and in a relatively short amount of time. One of the biggest problem of the additive manufacturing process, in particular, powder bed fusion, is the lead time of production. While the production of a part can take up to several days just to be printed, and then you have all the post-processing. This increased costs, in particular in times such as in the one that we are, where electricity and everything is, the price is quite high. And so we were not able to change the layer thickness, basically because laser thickness is due to the movement of the base plate before the recoater passes. And so you cannot change, I mean, you cannot print several specimens with different layer thickness, basically because it's just the movement of the base plate, and so is uniform for all the base plate. And also hatch distance enter in the geometric parameters of the printing, and so can go ahead with the layer thickness. You can change hatch distance depending on the specimen, but it's more geometric characteristic. And then we have the laser power that we want to maximize, because maximum laser power will go with a maximum scan speed, because in general, the problem with hot cracking in printing parts for superalloys derive from the fact that you are continue to give you energy to the system. And so secondary phase that in general are the system such, okay, let me introduce again. Superalloys are alloys with a matrix that is made of nickel, or in general nickel cobalt, that you strengthen by the use of secondary phase. That could be carbides or could be secondary phases such as gamma prime or gamma second. The presence and the coherence of this secondary phase introduce the high strength characteristic typical of superalloys. The problem with additive manufacturing this kind of alloy is that if you continue to give energy to the system, the secondary phases grow, reaching a point where they are not coherent anymore, and so they are introducing stresses. And then when the melt material start to solidify, you will have some point the right quantity of energy in the right time to avoid the overheating of the system. So if you reduce the power, you will probably need to reduce the scan speed. And so we are not obtaining the high productivity that we want to reach with this project and in general with the low power bed. So in general, we have print some specimen changing the scan speed. And you can see in the graph on the right that as the scan speed for the ring shaper go up and the density decreases. And what we have observed in following metallographic analysis is the three main defects that you can observe due to additive manufacturing process, where you can observe a lack of fusion. That is the biggest porosity. Basically, it's empty material due to the fact that you don't have a correct cohesion between powder or between different layers. And then you have a circular porosity, uh, again, correlated to the fact that you don't have such a good um, such a good cohesion between the part and the powder, and you can have some gases trapped inside. And then starting from one point that is critical, so the edge of the lack of fusion, a hot crack starts, basically because you have some stresses that are increases by the presence of the um, for the case of Inconel 929 gamma prime phases that is grown out of control, and it has created more stresses, leading to hot cracking. The only result that was really good was at the lowest scanner speed, that was 550 millimeter per second, where we reach a density of 99.9% and no presence of hot cracking. Following to the ring shaper, we go to the top hat, where we have way more good results. In particular, we have tried with the same parameters as for the ring shaper, and we have tried different scan speed. This time we have observed no cracks in any sample for any different scan speed and very low porosity. That is just circular. That, let me say, it's the last dangerous defect for additive, because you are not introducing any edges that can increase uh, the stress concentration. So, and in particular, the lowest one was 99.7% of density of the material. So starting from this preliminary job for both the shaper, we wanted to observe if laser beam shaper will introduce also uniformity on all the base plate. So what we have performed, it was to print several specimens around the base plate with the best parameters that we have found in the first approach, and see how the mechanical properties changes and how the repeatability of no cracks and high density is obtained. Particular for the ring shape, we have used the 550 millimeter per second scan speed, and we have seen that we can reach a high uniformity. As you can see in the 5 specimen that we have print, we have no porosity and no cracks at all. Then this is just this is not a crack. I don't know if you can see my mouse, but this is not a crack. And another important point that we have taken account is the welding spot. Well, it's not a real welding spot because we are not welding, but the spot of the laser. For the ring shaper, it was quite high, 500 microns. And this will lead us to some consideration that I will do after the presentation of the results of also of the top hat. For the top hat, we have chosen the higher velocity, scan speed velocity that we have found with a higher density. And so 920 millimeter per second. And we have seen again the repeatability of the application of a beam shaper on a laser powder bed fusion machine. Because again, we have no cracks and no porosity at all on all the specimen around the base plate. This time, the laser spot is half of the one of the ring shaper. And then we also have performed some mechanical testing, in particular at Tensile, in both the direction of additive manufacturing. Again, additive manufacturing, since you are building layer by layer, you have a kind of anisotropy on the sample. And so in general, what you test is both in both direction. And so this is the reason why we have testing in X, Y, and Z direction. And then we have compared the result that we have obtained with the expected one. While for the expected one are the result that we have observed print in increment 939 on your machine that we have inside. In general, what we have observed is a decrease in mechanical properties of roughly 100 megapascal, that it's not that much considering that this part needs to be heat treated at the end. But this decrease in mechanical properties correlated to the fact that we have no out cracking and correlated to a small laser spot will let us arrive to the consideration that what we have done to the system is to give an energy that is lower to the point. So we have formed a less quantity of gamma prime phases in this manufacturing production that have a lower strengthening effect on the material, and so have reached to a slightly lower mechanical properties, but also to no hot cracking. Considering that this part is generally heat treated at the end, it's something that it's perfectly fine, and it's very, as I can say, a very good result, because we have print. After that, what we have done is printing another job that you will see in the next slide with a small part to see if we have some cracks, and we don't have any cracks. So at the end, the result will be that without beam shaping, we have cracks and we have porosity. And this consideration is valid both for the machine that we have used for printing in this project, so the EOS M280, but it's also valid for what we print with newer machine, for example, M290. And that in general, we observe cracks. And so following to that, we perform hipping, for example, to remove that. Instead, we have crack-free both for top hat and big beam. And then we have porosity without the beam shaping. Instead, here we have no porosity. We have a finer mix structure in the top head, leading to the consideration that we have probably generate less structure that will introduce fragile effect. And the mechanical properties are closer to the one that we obtain with newer machine, but with the cracks. This is, as I told you before, what we have the validation job. And unfortunately, we were not able to print a fully complete part, basically because it requires several days, and this was a short project. So if we have some troubles with the printing, then we need to start again, and this will introduce some. We will probably run out of time. So this was just a part, but the idea that we have print a part that is completely cracks free, that is completely full dense. It's in Incon 939 with an old machine. It's a really nice result. And again, I take the microphone. Give the microphone to Gwen again, and thank you for the attention.
Thank you, Simone, for this very nice presentation. I'm so happy you are actually with us, because I would definitely not be able to give so many details about what was actually done. So is my mic working well? Clementine, can you tell me? Yeah, should be. Okay, perfect. So we are actually reaching the conclusion. So it's actually perfect timing. Conclusion of the project, AMLabs. Well, I think we are happy that we have somehow demonstrated that beam shaping was working to print Inconel 939, and that it can actually improve the quality of the printing process. We are actually paving the way for post-processing reduction or suppression. We didn't demonstrate it. This is like still something which has to be done, but we have actually confidence that it is actually working. As actually Simone was saying, this project had to had an end. We are having limited budget, so we couldn't demonstrate that, but we will be doing that soon. So what are the next step then? Well, actually, the idea is that what we have demonstrated that we could do retrofit of existing machine actually to increase the list of the printable materials with one machine, which is maybe not capable of printing that one material. We could actually integrate that also in the machine on some new machine as well, of course. We want to carry on actually development with Presix. Now that we have actually enjoyed going to Italy and work with you, we hope that it's going to continue, and we will actually be studying, I hope, more complex part, like real parts. Actually, that would be actually pretty nice. And we have actually to evaluate what is the impact on the post processing. So that's something I hope we will be doing also in future. I want also to say one word about the future of beam shaping for LPBF, I would say in general at KLabs. So I will be talking a bit on more short term and somehow on more long term. In the short term, we have learned so much inside this project. It's been really a very important project for us. And now we have a better view on what has to be done on the LPBF and what we plan to do in the next few months is, and I'm really saying in the next few months is like it's going to come very soon, is actually to have systems focused on two topics. We will be looking, of course, at yield improvement because it's a huge challenge of the LPBF world. And what we believe is actually working for that is to have some kind of ring shape that is enabling a faster printing of the inner of the parts. You have a larger ring compared to the Gaussian beam, and you go faster because you increase the hatch during your printing. And then you have to switch back to a small Gaussian. That's what somehow we feel will be working fine to do the contouring. So right now we are working on having that really fast. The target is 10 milliseconds for the switch in between both shapes. And actually in parallel of that, we will be actually looking at hot cracking reduction because this is what we demonstrated inside that project. And this is probably working better with TOPAT. So we want to generate actually a TOPAT, and we want also to be able to switch back to Gaussian. Why that? Well, there will be parts that you want to do with the Gaussian just because somehow your customer validated the process with the Gaussian. So you have to get back to the Gaussian as well. Having something static is not working, but probably on that system, it might not be needed to have so fast switch. So we will be looking at a solution which will be simpler to implement, and that will be somehow slower, very probably. But we could do anything. This is what we have in mind, what we plan to test. I did say ILT, so we hope that we will be working with them this year. We will be working with some other partners also to develop those systems and test them. But we could do much more than that. And I want to say everything that we can do because it's important to say it. You can contact us, and we are actually ready to work on this topic as well. We could do any kind of shape. We did discuss some of this shape, but we could do, if you think a triangle could work, well, we have done triangle on other application, we could do it. And we can actually really try to have the best intensity profile for your process. It can be what is on that side, but it can also be something else. We have to actually we could actually, I would say, adapt to any input laser you're having. So we've been working with some laser. IPG is pretty spread on the market, but it can be actually any laser. We are actually very happy to work with any kind of laser. And of course, this system also was just made to do some tests with actually Presix, but we can customize also the mechanical footprint to your machine so that it's actually really fitting better whatever machine you are using. We can handle multiple lasers. It's just a basic, simple sketch of how we could do it, but there are other ways to do it. But I think the more the laser, the more the interest of beam shaping as well. And we are definitely working on increasing the flexibility of our system. So it means having this bypass, which is a must, having the adjustment, the dimension adjustment of the shape, having multiple shape is also something we will be looking at. So I did say the top hat for something, the ring for something else. We can have a system having the Gaussian, the top hat, the ring, and others. It's just that the more the complex, the more time we will need to develop it, I guess. But this is something we have in our mind, and our technical team is working on that already. And dynamic change of the shape would mean that, for example, ratio tuning in between two subshapes is something that we can actually also work on, and that we did in another project, which was a Horizon Europe project with Ayman called Custodian. Okay, so I think it's 10:44, so we actually have to go to the Q&A session. So I just have a small stop on our emails so that you can take enough time to write both Simone and my email if you want to ask other questions in future, but we will get to your questions that are in the chat. You can keep asking questions even when we are answering the question. They will appear after we answer the first ones. So let's go actually to the Q&A mode, and it should actually show the one question. Okay, so what we will do is that I will be reading the question, but some of them will be for me, some of them will be for Simone, and we will try to improvise who is answering. So have you investigate solid state cracking in actually, it was not the first one. So I will just try to, get back to the very first one, which was that one. Okay. Can you also modify polarization of the beam from linear elliptical to circular or radially polarized? So this one should be for me. We could. We haven't done it inside that project. We would do it probably very similarly as anyone would be doing it, using some components which are available on the market to tune the polarization. It can be definitely inserted inside the system. It can be something which will be flexible. Like, for example, you could choose it by programming something so that you can pick up the polarization you want. So just, yeah, let us know what you would be needing and we can definitely consider it. Next question, how do you handle the absorbed reflected laser power inside your optical bulbs? This is an absolutely great question. We don't, for now. In that case, the transmission was actually quite good, more than 90%, I think more than 93% to be exact, and we were handling only 200 watt. So those 7% of 200 watt that are spread are manageable by the system itself. It's just gonna, yeah, maybe heating up a little bit, but it's okay. But what we have done on other application, I would mention, for example, laser beam welding is handling a lot more power. We have actually demonstrated that we can handle 24 kilowatts. So nobody will never use 24 kilowatt in LPBF. But just to say that we could handle that power, and of course we were having a strategy in that case, which was water cooling. So as soon as we will go to 500 watt on LPBF, we will water cool the system and it's going to work perfectly fine. Water cooling of reflective system is actually extremely convenient compared to lenses or whatever refractive optics, because you don't have to actually cool down by the edges of the lenses. You can actually cool down by the back of the mirror. So it's very homogeneous and it's actually working fine. I'm speeding up a bit my talking speed. I'm sorry for that, but I know we actually have a lot of questions. So what is the wavelength limitation for MPLC, if there is any? No, there is no limitation, basically. So limitation is how much time we need to develop the system. And there are also limitation maybe on what shape you want to do for what process. But in the world of additive manufacturing, it's not an issue. Most of the process currently on metal is done with 1 micron lasers, which is somehow the one we master the best, because we have done a lot of 1 micron. We have done also lower wavelengths. We have done systems for microprocessing in green. So we could work with green laser if you want to do some copper printing, for example, with beam shaping. It is possible. And I would say also that we have a look at polymer. And we know that polymer are printing generally with CO2 lasers, 10 micron wavelengths. We have not done CO2 yet, but CO2 should be like a highway of success for us. Why that? The longer the wavelengths, the easier the optics are to manufacture. This is very general, because the same defect on the optics will have like so much less impact since the wavelength is bigger. So it will work. It's just that we have to develop for example, the process manufacturing, because it's going to be new material for the mirrors. We have to develop the control, because controlling in CO2 with a beam at 10 micron is not easy. You don't see anything. There is no camera. But we will definitely do it soon to work with CO2. I say I'm going to be quick, and I'm actually very long with each question. How about certification of the system with this implementation? Okay, I'll try to answer fast. I guess that certification, you mean that probably Simone has scaled the warranty of his machine with our beam shaping being installed. Yes, and the good thing is that the machine was not under warranty anymore, and that's somehow a problem. Yes, I cannot say no, it's not a problem, it is. So I would say that if we work on retrofit, there are two ways. Either we don't care about the warranty of the machine, either we have the machine manufacturer inside, and I actually hope we will be for option 2. But it is obvious that the one way this is like really spread all over the world is to work with the machine manufacturers, because they have to integrate the system, they have to pilot the beam shaping. I am saying you have to switch in between two shapes. How you switch? You have to switch inside the machine. So it has to be the machine which is linked to the beam shaper. And definitely you have to change your printing strategy in the long term if you really want to have good results with beam shaping. You want to change the printing strategy. This is inside the software of the machine. So collaboration has to be good with the machine manufacturer. That's for sure the future of LPBF for us. Okay, one for Simone. What was the focus beam diameter for the M280? I guess they mean when it was in the Gaussian mode, and I have actually no idea on that.
Unfortunately, I don't have idea neither. So if you send me an email, I will take the information. I will respond by email. So unfortunately, I don't remember. I'm sorry.
Okay, no problem. I guess actually we will have the email of the attendees, and we will find your
Okay.
email and answer you by email. What is your hypothesis on the physics metallurgy of the crack mitigation? Why would it not crack?
Well, the hypothesis is that unfortunately we did not have enough time to perform enough studies on that. The hypothesis is that we were able to give energy for a less amount of time to the system. In such a way, we have developed less amount of, in this case, gamma prime phases. That is the one that is, I mean, this hypothesis lead to two different considerations. The first one is that we expect with this hypothesis to have less strengthening effect on the material. And in fact, we have lower mechanical properties with respect to the S-build condition with some hot cracks. And we also have a lower welding spot dimension, meaning that probably what we have reached is that we have a more specific effect of the welding of the laser in one point. So for less time, we have less amount of heating for all the phases, and so we have developed less amount of gamma prime phases, and so less fragile effect. And also, I don't probably focus too much, but on the results, what we have observed is roughly 1 megapascal less in ultimate tensile and also in yield strength, but we have observed roughly 8 or 10% more in elongation at the end of the specimen, and so this leads to the same consideration. We have a less fragile system. I hope this has answer enough to the
It's so
to the
great you are
question.
here to give this detailed answer. I would definitely not be able to do it. So thank you, Simone. I think it should be perfect. So what scan strategy was actually used? If you do remember, Simone.
Yeah, I mean, the concern was in particular for the elliptical that has the two different dimension depending on, and in that way was we try in both direction, but for the other one it was rotational. I mean the Yaras are symmetric, the other shape, so I think it was rotational. But
Okay, cool. What about the spatters formation with these different beam shapes? Have you also tested the performance of this device with higher layer thickness?
and no, we do not have in general, because again the time was not too much, and we wanted to, I mean, we are not printer producer, we are printer utilizer to produce finite parts. So the idea was to stay as much as possible to the parameters that we use, and in general performing different jobs with different layer thickness will increase a lot the time and also the costs. And it's something that we need to investigate. It's something that it will probably go inside the following studies around the beam shaper, but we don't have try with a higher layer thickness for these reasons.
I'm so happy. Actually, a lot of people seem to have actually a lot of ideas of things to try. Please do contact us. We are happy to try everything. Actually, we have to somehow. What about the difference in achieved productivity in between top hat and ring shape? From Martina.
Well, the difference in productivity is it basically is based upon the scan speed. While in our cases, with a ring shape, we have obtained 550 millimeter per second, while for the top hat, it was 920. And so in general, the increase in productivity with the top hat was more than 60%. And it was really close to the one that to the scan speed that they following using on your machine.
As I said, for I think the main focus was mechanical properties, if I'm not wrong, Simone. And I would say that stay tuned. We will be really looking into productivity in future. But you cannot. I mean, it's different topics somehow. So we have to have different strategy if we are just focused somehow on the productivity. So we will do it, I guess, soon. June, my target. So beam diameter for the M280, we were not able to answer, but what was the beam diameters for the other shapes? Elliptical, I can't remember because in the end, elliptical anyway didn't work, but the top hat was 90 micron and the ring was 150 micron diameter. Have you investigated solid state? Okay, we are getting back to that question. Solid state cracking in post-processing or any of the hot crack free samples? Simone, for you.
We have not investigated post-processing. Basically, the consideration about the reduction of post-processing was based on the avoid the hipping process. Currently, we perform hipping basically because we want to achieve a full dense component with no cracks. And what we have observed is that on specimen and on simple components, we have reached fully dense, higher than 99.9% of density, and without hot crack. So the consideration about post-processing was on this point to avoid eventually hipping. Unfortunately, we do not have investigated anything regarding the post-processing because it was out of the scope of this project. And again, we don't want to run out of time, but this enter inside. Uh, I mean, what we expect is that in general, mechanical properties at the end of the post-processing will be closer to the expected, um, so more closer to the expected one with respect to the India's build condition. And we also need to investigate the solid state cracking in the post-processing. This is again another point that we need to follow up after this project.
It's cool that there is so much to follow up. So 2 minutes for the question left, and I have 4 questions. I see still 4 questions. So I will be very short. Are you also planning to test or have already tested the beam shipping effects on other difficult to weld materials such as Inconel 738? We Labs are taking any inputs on what would be the powders to be tested and what are the most important powders to be tested. I had actually a survey number 6 or 5 anyway on the powders that you think are very interesting to look at, but I couldn't make the whole list, so I just gave up on that one survey. But send an email on what you think is very important, and we will have a look at that. And I'm also sure that actually Presex is very interested in that. What about the sorry, that one. Can the beam shipping tool survive long, non-stop, multi-day prints without damage or wear? Yes, it has to. And the fact that it's actually reflective is actually helping somehow the surviving and all that. Have we already stressed the system that much? Not yet. We have to do it for sure. And I'm happy that we have the answer, so we don't have to answer by email. Standard spot size is actually 85 to 19 micron.
Thank you very much.
Thank you. Yes. And that's the last question. Great. It's 10:58. Can you show the video showing the smoke spatter behavior? We will send it to you by email. Actually, this tool that we are using with webinar is not ideal for the videos. It's possible to do it, but it's not ideal because actually when we upload the slides, it's in PDF. It's not in PPT, but definitely we have the videos. We will send them. So it's perfect because we have answered all the question. So getting back to our emails so that you still have some more seconds to write them down. I'm absolutely so happy, Simone, you managed to make it for that webinar with us. It's been a great project, and I'm really happy that we could do this webinar to kind of end it.
Yeah, thank you very much for the possibility to be here, and thank you everyone to listen to our results. And you have our email. You can write for anything. Also, more questions. Um, at least from my side, you can just write down the question. I will answer you in the next days.
Okay, thank you all. Have all of you a nice day, and we definitely keep in touch by email. Bye bye.
Bye.